Hello everyone, my name is Patrick, and today I'm going to present TeTRIS, which is a general purpose fuzzer for finding translation bugs in source-to-source transpilers. So as a quick summary, TeTRIS is a fuzzer for transpilers. Transpilers are a popular language upgrade tool for translating from one language to another. However, these often create subtle bugs when you do the translation, and random fuzzing does not often capture these subtle bugs. So TeTRIS aims to find and explore them. So to start, let's introduce a few concepts. So first, what is a transpiler? We all know what a compiler is. Compilers translate a programming language into assembly and ultimately into the final binary. Transpilers are a compiler, except instead of going from a language to assembly, they go from one programming language to another, such as, C to Go or C to Rust or some combination. So why would you want to use this? So languages change over time, and with these changes comes the need to make upgrades. For example, a lot of legacy code is written in really old languages like COBOL and Fortran and whatnot. However, doing this is very time consuming and error prone. You need someone who understands both languages and has a fair grasp of the algorithms of both languages, and the programs they're translating as they do this. And this is, as you would expect, very time consuming and error prone. So having a way to automatically do this is desirable. Fuzzing is a method of finding bugs by giving programs random inputs. And the idea here is it's meant to be like another form of testing in your test suite. It's meant to supplement the regular unit testing that you might use to find bugs, and the idea behind fuzzing is to specifically find crashing bugs, since crashes can be used for some pretty nasty security exploits, along with just being inconvenient and whatnot. There are a few types of methods for fuzzing. The simplest is black box fuzzing, where you do not have any knowledge of the program you're fuzzing, you're just throwing inputs at it. White box fuzzing is when you have full program knowledge and you can, trace your way through the program as you throw invalid inputs at it. Gray box fuzzing is a fuzzing method that kind of sits in the middle. You may have knowledge of like your source program, for instance, but there may be proprietary libraries that link to it, and you can end up with scenarios where maybe a crash occurs in the source program, in the source that or it occurs in the library. So when we combine fuzzing and transpilers, fuzzing is a good way to find bugs that arise from errors in the transcompilation. However, just shooting any random input at it doesn't make sense. We want to find bugs in the transpiler itself, not bugs. We want to find bugs introduced by the transpiler in the translation process, not just bugs in the actual transpiler. And going back to our previous slide, for this we want some kind of gray box or white box testing. Alright, so with those core concepts out of the way, let's dive a little deeper. So, transpilers. As we've said, a transpiler translates one programming language into another. The key here is translation, not compilation. And this is not like an altogether new concept. There are languages in production that compile from one language to another, a notable one being TypeScript, which compiles down into JavaScript. But this is not like the only source of it. A huge reason for transcompilation is stack migration, which is where we go back to things like moving a software stack from COBOL or Fortran into a newer language that's better supported on modern software stacks and known by more people. So transpilers are relatively new, but there are several that exist for things like C to Rust migration, C to Go, or other really modern languages like Zig and Nim. And then there are other languages that take kind of the TypeScript approach of compiling into another language, but compile to several different languages such as Hax, Fusion, Dart, and so on. So how do transpilers work? So obviously your input's one programming language, your output's another programming language. But when you take an input programming language, you first translate it into the source language specific AST. This AST is translated into like an intermittent universal AST. And after some instrumentation and other stuff is done, it is lowered into the target programming language. And we'll go through these steps in a little more detail now. So, the source AST translation. This is the first step. Every compiler does this. This is when the source language is translated from textual tokens into a machine readable graph called an abstract syntax tree. The AST is annotated to remove language ambiguities, such as assigning concrete types to inferred types. And this part of the process is specific to the source language. So even though we're parsing this into something that is machine readable and understandable, we cannot dump this into our target language just yet. So because of that, we get to step 2, which is our intermediate or universal AST. And the source AST, the source language specific AST, is translated into our intermediate or universal AST. And this is more of like a universal, more verbose AST. The idea for these ASTs is to be language agnostic, to generally represent language constructs, and to prepare them for whatever language that we are translating them to. Step 3 is when we do stuff on our universal AST to prepare it for the target language. Various passes and optimizations are performed, and what these look like are very dependent on like the source language and the target language. If we're going from something relatively simple such as C to something more complex or verbose like Rust, the universal AST has to be altered and prepared to meet the more complex and deeper structures that are inherent in Rust and other similar languages. And then finally, target code generation. The universal AST is translated into the target language, and if all is good, hopefully this will be done correctly and we'll have a ready to go translation ready to compile and use. However, this, as with any program, this is not always as perfect as we would like. There are several ways that a transpiler can introduce errors. The first and most obvious is syntax errors, and these result from differences in the language structure that the transpiler may incorrectly translate and lower and introduce errors in the generated code. Type conversion is another huge source of errors. Types, probably more than anything, vary across languages. These are hard to translate, and when we're going from a language such as C that has a relatively simple and flexible type system to, Rust or Go, which has a much more strict set of type definitions, it's pretty easy to mess these up in some ways. And this can be syntactically, meaning it's caught at runtime, or this can be a more subtle error, such as using a type that is smaller than what the original source type was supposed to be. Another type of error would be missing code. Transpilers could misunderstand the meaning of a certain section of code, and then just drop it all together. And this is not always as easy to see as you might think. This could be a very subtle thing that doesn't cause like any kind of compiler error, but crops up at runtime and introduces like state differences and other errors. So the bottom line here is the big problem with transpilers is semantic errors. Syntax errors are generally easy to catch and correct. These are caught at compile time, so if you're transpiling from one language to another and it introduces a syntax error, the destination language compiler will throw an error, and you can make appropriate changes, update your unit tests for the transpiler, and we're all good. Semantic errors are the insidious ones. These are usually correct syntactically and may run correctly or appear to run correctly in most cases, but they can cause differences in state and runtime behavior. And this could potentially cause crashes, ranging from inconvenient crashes to some pretty significant security vulnerabilities. All right, so with that out of the way, let's dive into the motivation for this work. So the big problem with fuzzing a transpiler is it often just turns into compiler front-end fuzzing. So if you take like a grammatically correct English sentence, there's a couple of ways you can change it, and at best this shows that we can catch syntax errors, and yes, we need to do that, but all this shows is that we can parse the input correctly or incorrectly. It doesn't necessarily show whether or not we can translate it. And as an example of this, for semantics, a good parallel is like translating human languages. And I have a little French phrase here. It means the man watched a film, it was good. Now, in English, we understand what that means perfectly well. In French, nouns have a concept of gender, so the gender of the pronoun used depends on the noun that it's referring to. Now, most of us would, so this phrase could translate into two ways. The second sentence, il est bien, it could mean the man is good, or it could mean the film is good. Syntactically, either of them are correct. Semantically, it's kind of unlikely that we're going to refer to the man, given that we're talking about the film. So if this was translated into the man is good, that would be kind of weird and not correct. But if we translated it as the film is good, then we have a correct translation. And these kind of semantic things are the things that we want to fuzz and try to catch within the transpiler. So, to kind of narrow this down a little bit, once again, we don't want to fuzz just the front end. We want to get at the core semantic translation logic. And this would be, to go back earlier to the compilation process, this would be at the part where we're translating the source AST to the universal AST, doing whatever on the universal AST, and then putting it back into the destination language. So that is what we want to test in fuzz. We also want this to remain language agnostic, so we can use it on existing transpilers, test existing transpilers. And again, we want to test this on real world tools. We don't want to just invent a transpiler with a built-in fuzzer in it. That would not be particularly useful. So with that out of the way, let's discuss the design and implementation of TeTRIS. So TeTRIS operates on the intermediate AST. This intermittent AST is mutated in specific and defined ways. After that, the compilation steps resume, and testing of this is done by comparing the original binary with the transpiled binary. So that's kind of what TeTRIS does from a high level. We'll now discuss this in more depth. So the first step in TeTRIS is source code mutation. And keep in mind, we want this to remain language agnostic, so we don't define a bunch of grammars or stuff like that. The idea here is that the input for TeTRIS would be a corpus of seeds, and these seeds are a collection of source code in the original source language for the transpiler. And this will first be parsed to populate an internal dictionary of valid code structures, and these code structures will be mutated and resolved to create an input. Once this input is parsed and understood by TeTRIS, TeTRIS will apply a number of different mutations that will mutate different parts of the structure of the language in different ways. Here's to the left is a list of the different mutations from the paper, and you can kind of see that they range from anywhere to mutating something very specific, such as an arithmetic or a logical operator, to stuff like replacing literals and variables with other literals and other random values, changing casts, swapping the order of statements, or deleting an entire statement altogether. And since this is fuzzing, we want to randomly apply these, so these different mutations are randomly selected and applied to the input program based on the seeds that we know. After this is done, the next big thing that we want to mutate is types. Keep in mind that a huge source of transpiler errors comes in type translation. And there's a couple of different ways to do this. One way is to change scope visibility. Different languages have different rules about variable visibility, so it's possible to reuse variable names but use different types, and then these, despite having a similar name, represent something totally different in memory, and all different things like that. It's very dependent on what the language is, and since it's dependent, there's a lot of rules in how this is translated, so we want to change scope visibility. We also want to mutate types in ways that are syntactically correct but semantically wrong. And one example of this would be if I have like a 32-bit int in C, this must be translated to a 32-bit int in my target language. If I accidentally translate this to like a 16-bit int, I'm going to lose the upper half of my precision, and even though this is syntactically correct, this could create a number of runtime errors and crashes. So once the syntax is mutated and types and scopes are changed, we can insert instrumentation. And this goes back to our earlier discussion of the different types of fuzzing, the black box, gray box, and white box fuzzing. And the idea here is that as we're fuzzing, we want to understand where these errors are occurring. And because we have access to the input source code and the output source code, we can instrument it so that when we fuzz it, we can have an idea of where the errors occur. And there's many different ways to do this. TeTRIS does this by using the language-specific variants of printf. Most modern languages have some version of printf built in, so this provides a common method to capture the runtime state as the program executes. And this is something that occurs right before target code generation when we're still in the universal AST. So now that we've generated our test inputs, how do we identify the bugs? There's a few ways to do this. The first one is runtime divergence, and this would be like if we're running the two programs with the printfs in them, And if they start displaying different intermediate values, such as if we're doing an arithmetic calculation and the two programs running start displaying different intermediate values from the calculation as it goes on, as the program executes, then that means some kind of a translation error has occurred. So this would be the runtime divergence. Post-translation failures is another one. This is when more obvious errors cropped up that can cause compilation errors or runtime crashes. Both of these would be much more obvious translation stuff that would be caught at either compile time or fairly easy to catch through debugging at runtime. And then, of course, there could be bugs within the transpiler itself, like if it does not handle a certain mutated language construct correctly or type difference correctly. We don't want the transpiler to just crash. We want this to gracefully exit and tell us what the error is. So, certainly any bugs in the actual transpiler itself unrelated to the translation process are always good to get. So, with all that having been discussed, let's see how TeTRIS did in its evaluation. So, let us begin by talking about the experimental setup. The authors tested 7 real-world transpilers. This provided a number of different language combinations. We have C to Rust, Go, and Zig. We have Go to Hacks. We have Hacks to C++ and Python. The C to Go occurs twice, but it's 2 different transpilers, and C to Go is a common translation target, so hence why they included 2 of them. In terms of previous fuzzers that have attempted to fuzz transpilers, the authors compared against 4 language processor fuzzers, Polyglot, AFL compiler fuzzer, AFL++, and CSmith. As much as possible, they use gray box fuzzing with the transpiler to have the instrumentation, but when that option was not available for whatever reason, they just used black box testing. In terms of source code generation, CSmith was used for the C programs, and then various iterations of it were used to generate random source code for the other input languages. The authors made custom generators when tools for generating random source code was not available. One of these languages was Hacks. In the evaluation, the authors ask 3 research questions. First of all, is TeTRIS effective at generating valid inputs? Secondly, can TeTRIS thoroughly test these existing transpilers? And finally, and probably most importantly, does TeTRIS actually uncover translation bugs? In terms of the first research question, can it generate valid test cases? TeTRIS scored very high with this. In terms of generating valid test cases for C, CSmith did the best, but CSmith only works on C. AFL++ and AFL compiler fuzzer could generate random inputs, but the valid test cases that they generated, the number of valid tests from the source code was very low, hovering at like 2 to 3%. Polyglot got around 11%, but didn't support Hacks. TeTRIS worked for all of the language inputs and scored very high on the number of test cases that it generated. For our second research question, the code coverage, once again, TeTRIS scored very high in the code coverage and generalizability. This table shows the amount of extra code coverage that it was able to achieve compared to the other fuzzers. Polyglot scored well, but it did not support all the transpilers. Once again, AFL compiler fuzzer and AFL++ were generalizable, but in both cases, TeTRIS scored 20% higher than either of them. C-Smith again did the best in terms of coverage in this metric. They actually scored about 10% higher, but once again, C-Smith only works on C, so even though it does well with C, it's not as generalizable. And then finally, the big question, finding transpiler bugs. And this is where TeTRIS has a clear advantage over all the others. Of all the other fuzzers tested, only C-Smith found other bugs, which is why this table only shows TeTRIS and C-Smith. However, C-Smith only found known bugs in the C-to-Rust transpiler. It didn't find anything new. TeTRIS not only found 4 known bugs, it found 12 new bugs in different transpilers. And TeTRIS found a rather diverse array of bugs. As you can see here under the bug type column, it found syntax bugs, it found type conversion bugs, it found cases where code fragments were dropped or mutated to a point where runtime diverged or translation failed, and it found a variety of different bugs pretty much on all the different on all the different transpilers. And as we said in the previous slide, most of these were new bugs. So, in conclusion, as the authors concluded, they identified a few areas of future work. The big one is support for dynamic languages. As you may have noticed, all the languages they tested on were compiled languages, so testing stuff between 2 dynamic languages would be very interesting and very useful. Support for more advanced language features was a wish list for them. A problem they found was TeTRIS did not do a very good job at handling undefined behavior. And then finally, the authors would like to see higher numbers of test cases generated from the input corpus. So in conclusion, TeTRIS demonstrates great potential in finding transpiler bugs. It shows that they can fuzz the transpiler translator itself rather than just the front end. They demonstrated that they can support a diverse set of language combinations. They can achieve high code coverage. And to round it all out, they found 16 bugs total, with 12 of them being new. So that concludes our presentation. Thank you very much.